Decided that we would wait until today to go over it. So take a couple minutes and with somebody next to you, try to work through this. What is the partial pressure of carbon dioxide in the atmosphere? And carbon dioxide is present at about 400 parts per million in the atmosphere. And let's say the total atmospheric pressure is 1,000 hectopascals. So take a couple minutes and think about that.
Just multiplying the 400 by 1,000.
Yeah.
Percentage because when we did, or so like when we did
Like $100 is always like up here.
Mhm.
Like $80 for this exam.
how much nitrogen is in the air now?
Yeah.
Do you want me to do this as well? Do you want me to both that as well for that same time?
Hectopascals?
Sure. Yeah.
I did it on,
What, that's Scotia, right?
I started.
we do 1,000 grams for 400 parts per million, but we have to like.
So you change the parts per million to something.
I think I actually have Saturday.
Okay.
I think that makes sense because carbon is like 20.
Being a two conversion, I'll tell you whatever.
Yeah, no, I was just saying that.
I think that makes sense.
400 by 1 million,
I'll roll with
take
it.
your mole fraction and then multiply that by 1,000.
Oops.
Yeah.
Whoever watches this is gonna pick up the audio. It's gonna be like-
I erased my notes, so I don't have.
Oh yeah, Tori's gonna listen to it and be like, what were they doing?
I think you'll appreciate that.
Okay, I think maybe in the interest of not staying too late, let's go ahead and work on this now. Okay, so this is asking what is the partial pressure of carbon dioxide? And the key thing to recall is that the partial pressure of any gas is closely related to its mole fraction by Dalton's law. And so if we write this down, the partial pressure of carbon dioxide in the atmosphere is equal to its mole fraction in the atmosphere times the total pressure. Now this is true for any gas, but so we're just doing the calculation for carbon dioxide. Now, we have over here 400 parts per million. That means that 400 out of every million molecules is carbon dioxide. So we could rewrite this as 400 times 10 to the minus 6 moles of carbon dioxide per mole of air, or 4 times 10 to the minus 4 if we make it a little bit simpler. Now we can do the calculation. We have 4 times 10 to the minus 4 times the pressure, which is 10 to the 5 pascals.
It's so strange.
And you can do the math there. You end up with 40 pascals. Or, obviously, 0.4, a little less than half of a hectopascal. So carbon dioxide is a trace gas in the atmosphere, but it actually makes up almost half a hectopascal of air pressure or the air that we're breathing. Questions about that? I see some furrowed brows. Okay. Now let's go back, and if there aren't any questions about that, let's pick up and remind ourselves what we were working through on Wednesday. So on Wednesday, we were working through the difficult task of how to calculate the density of moist air. So that was the problem that we were trying to solve. And initially we had the problem of, we had to calculate the mean molar mass of moist air and then the specific gas constant for moist air, and then we were able to use the density form of the ideal gas law. But if you have to recalculate R every time for every different mixture of water vapor, that gets really time-consuming and tedious. So we came up with a different solution. This is, of course, the specific gas constant. It's not constant for moist air. So the name is a little bit ironic when you're talking about moist air. But we came up with an alternate solution. We said, we're going to do the calculation with the specific gas constant for dry air, and we're going to account for the amount of moisture in the atmosphere using virtual temperature. So the virtual temperature accounts for moisture. And specifically, we derived that in order for this to be true, the virtual temperature has to be equal to the air temperature times 1 for 1 minus the vapor pressure of water vapor over the total air pressure times 1 minus epsilon. And that's where we left off. We said, now if you know the fraction of water vapor in the atmosphere, you can calculate the virtual temperature, and then you can calculate the density. Okay. Any questions about the premise of what we're doing here? Now what we're going to do is we're going to simplify this. So everything we've written up to this point has been exact. We're now going to do some conversions, some of which will be approximations, and we're going to make this simpler to make it easier to calculate the virtual temperature. Okay, so the way we're going to do this is we're going to rearrange this to try to eliminate this PV over P. And specifically, what we're going to aim for is that we are going to express this. This is the fraction of air molecules that are water vapor. What we're going to do is we're going to introduce a variable that we're going to call W, and it's going to be what we call the water vapor mass mixing ratio. So the water vapor mass mixing ratio is one of the common ways that meteorologists express the amount of water vapor. And a mixing ratio is like a recipe. where it says, the recipe says, take 1 cup of sugar and 2 cups of flour and mix them together. This is like that, where it says, take 5 kilograms of water vapor, mix it with 95 kilograms of dry air, and that's your mixture. So the mixing ratio is the ratio of water vapor to dry air on a mass basis.
Will that be like in a problem that's given to us?
Yeah, I mean, we'll see at some point how you can derive it from measurements, but yeah, that would be something that would either be given, or it might be predicted in a numerical weather forecast model, something like that. Mhm. The nice thing about the mass mixing ratio is that it's the same when you just move the air around. So if an air parcel is moved and compressed or expanded, the volume of water vapor, the volume occupied by that, can be compressed or expanded, but the ratio of water vapor to dry air is going to be constant regardless of whether you compress it, expand it, move it up to the stratosphere. It's going to be the same unless you have condensation or precipitation to change the amount of water vapor. So that's why we deal with the water vapor mass mixing ratio. And I might put mass in parentheses here because often you will see it just written as the water vapor mixing ratio, or even just mixing ratio, because meteorologists seem to think that water vapor is the only thing that varies in the atmosphere. With my own specialty of atmospheric chemistry, where we're thinking about variability of all sorts of pollutants, that seems silly. There's all sorts of things that are constantly changing in the atmosphere, in addition to water vapor. Okay, so we're going to take the mole fraction of water vapor and we're going to express it in terms of the water vapor mixing ratio. And the additional thing that we need to do that is that I want you to remember that the mass of a gas is equal, like the mass of water vapor, is equal to the number of moles of water vapor times the molar mass of water vapor. So we have the mass is equal to the number of moles times the molar mass. And of course we can do the same thing for dry air. We can say the mass of dry air is equal to the number of moles of dry air times the molar mass of dry air. And with those preliminaries, we can now start working through this. We've said here that the partial pressure of water vapor divided by the total pressure, from Dalton's law, we know that this is just the fraction of molecules that are water vapor. So we can express this as the number of water vapor molecules divided by the number of total molecules. Does that make sense what we've done? Okay, now from here, we're going to use this relationship between the number of moles and the mass, and we're going to write something that initially looks more complicated, but then we're going to simplify it. Next, we're going to simplify this by multiplying both the numerator and the denominator by the molar mass of water vapor over the lowercase mass of dry air. And once we cancel things out, we have okay, hopefully it's clear which m's are uppercase and lowercase.
In the numerator, are those both lowercase?
They're both lowercase in the
Okay.
numerator, yeah. So I'll give you a minute to copy that down, and then we're going to recognize that each of these three terms is something that we've seen before. Okay, in particular, this here, the numerator, anyone recognize that?
W's.
That's W.
That's W, yeah. And so is this. So this is the mixing ratio of water vapor. Does anybody recognize this term over here? The molar mass of water vapor divided by the molar mass of dry air.
Is that epsilon?
Yeah. So this is a constant, first off, because it's the molar mass of water vapor divided by the molar mass of dry air. So it's 18 over 29. And we gave that value the special name epsilon. So what we have is W over epsilon plus W. Let me write that as more as a W so it doesn't look like an omega. Yeah.
For the middle one, why are we multiplying by the molar mass of water vapor divided by the mass of dry air?
This is one of those things where you do it because it helps you in the end.
Okay.
It's not something that you would necessarily look at this and say, aha, I've got to do this, but it is something where, in retrospect, you can see how it made sense because it gave us the water vapor mixing ratio. That was most of what we needed, and the rest of it's going to make more sense after that step where you might not have guessed what to do there. Now, the mole fraction of water vapor we can see is related to the water vapor mixing ratio in this way, and we can put that back in our expression over here for the virtual temperature. So I can rewrite this as so I've just substituted in. And now I'm just going to rearrange this algebraically to simplify it, and I'm going to do that by multiplying the numerator and the denominator by epsilon over W, or epsilon plus W, excuse me. So that gives me T in the numerator and epsilon plus W in the numerator. In the denominator we have, from this term, we have epsilon plus W minus W times 1 minus epsilon. And I'm just going to recognize here we have W times 1, so minus W plus W. These W's are going to cancel out. And so this is going to be equal to, well, I'll write it over here first. T times epsilon plus W divided by epsilon plus epsilon W And finally, simplify it a little bit more by pulling out the epsilon. Okay, so we've gotten to this point, and now we're saying the virtual temperature, instead of depending on the mole fraction of water vapor, now depends on the mass mixing ratio of water vapor. And we can go one step further and simplify this a little bit more. We have been exact up to this point. We've made no approximations, just invoke definitions. Now we're going to use one approximation. And I'm going to use this mathematical identity. If you take 1 over 1 plus a small number, that is approximately equal to 1 minus the small number. And this is true whenever your small number is much less than 1. So your small value delta. So we have something that maybe looks a little bit like that. In the denominator down here, we have 1 plus W in the denominator. Looks kind of like 1 plus delta. The question is, really, is W small or not? So let's think about that. W is the mixing ratio of water vapor, which is the mass of water vapor divided by the mass of dry air that it's mixed with. If I asked you, what's the range of water vapor content of the atmosphere, what would you say? 0 to 4? Yeah. So, yeah, on a mole basis, it's about 0 to 5%. On a weight basis, it's about 0 to 3%, maybe 4% in the deep tropics. Okay, so that means that W is always going to be less than about 0.04. That's pretty small. So I think we're safe doing this. We can do TV is equal to T times epsilon plus W over epsilon times 1 minus W. So we've taken 1 plus W out of the denominator, and we've made it 1 minus W in the numerator. And now we're going to multiply that out. So we have T. Everything is going to be over epsilon. And we have epsilon plus W minus epsilon W minus W squared. Just multiplying out those terms in the numerator. Okay, we made one approximation up here. Now we're going to use a second approximation. So we've argued that W is small because it's always less than 0.04. So we've got a W here, 0.04, say there. And then we've got a W squared. Well, if W is small, then W squared must be really small. So we are going to ignore this. And we're doing that with good reason. It's very small. Well, if we do that, then we can simplify this a little bit more. We can write that T is equal to 1, we have epsilon over epsilon plus W times 1 minus epsilon over epsilon. Then finally, we can look at this and say, well, epsilon is a constant. Epsilon is 0.622, the ratio of the molar masses of water vapor and dry air. Well, if epsilon is a constant, then 1 minus epsilon over epsilon must also be a constant, and it is. And it happens that its value is about 0.61. And this brings us to the form of the virtual temperature that you will see most often. And which you will mainly use for calculations. So the virtual temperature is equal to the measured air temperature times 1 plus 0.61 times the water vapor mixing ratio. So it's approximate, but it's a very good approximation. So if you wanted to calculate the virtual temperature exactly, you could use this formula or this one. But in almost all cases, your answer would be basically the same as using this approximate formula. Okay, with that, I want to work through a couple of examples and see how we use virtual temperature and why it's useful. Okay, so and we're going to look at this by considering 3 different air parcels, A, B, and C, because I'm really good at coming up with creative names. Okay, so parcel A is going to have a temperature of 30 degrees Celsius, and it's going to have a water vapor mixing ratio of 0.02. To be clear, that means 0.02 kilograms of water vapor mixed per kilogram of dry air. Or just kilograms per kilogram. Parcel B is going to have the same temperature, and it's going to be dry air. Parcel C is going to have a temperature of 34 degrees Celsius, and it's also going to be dry air. So if I asked you to look at these and without doing any calculations, can you tell me which air parcel is the most dense? Or the least dense? Yep.
I'd say most dense would be B.
Why do you think B?
Well, it's a lower temperature and has dry air. That's like I know that to be.
Right, okay, yep, good reasoning. Okay, so you've said B is, well, there are 2 of them that are 30 degrees Celsius. And this one has moisture and this one doesn't. So that's good reasoning. The dry air is always going to be more dense than moist air at the same temperature. Okay, so that makes sense. B is going to be the most dense. Can we say which one is going to be the least dense? It's hard. Because we know this one's going to be less dense than B. A is going to be less dense than B, but we don't know how it's going to compare with C, because this one has water vapor and this one doesn't. If we compare B and C, they're both dry, and this one has a warmer temperature, so B is going to be more dense than C. You can see that it's hard to compare densities, when you have varying amounts of water vapor. But that's exactly what we came up with virtual temperature to solve, to make that comparison easier. So what we're going to do is we're going to calculate in each of these three cases what is the virtual temperature and what is the density. Okay, so for A, we have the virtual temperature is equal to, well, as always, we have T times 1 plus 0.61 times W. So don't write this down just yet, but what if I put in, okay, so temperature is 30 degrees Celsius, 1 plus 0.61, W is 0.02. Don't write that down just yet.
And we're doing
Okay, does that look good?
We're doing A first, right?
Yeah, we're doing A first. Yep. I'll try to keep them all in the same columns. How does that look?
Temperature's supposed to be in Kelvin.
Yeah, so when we talk, we often talk in Celsius. When you do a calculation, gotta put it over into absolute, or in Kelvin. So 30 degrees becomes 303 Kelvin. Your virtual temperature will be off by a lot if you try to do it in Celsius. It won't work. Okay, so now we can do the calculation, and we get a value of virtual temperature is 307 Kelvin for air parcel A. And I'll just remind ourselves that the density is equal to the pressure divided by specific gas constant for dry air times virtual temperature. So now that we have virtual temperature, we can use the density form of the ideal gas law. So the density here is going to be equal to the pressure. Oh, I forgot to give the pressure here. We're going to say that all of these all at 1,000 hectopascals for simplicity. So we have 10 to the 5 pascals in the numerator, divided by, in the denominator, we have 287 joules per kilogram per Kelvin times 307 Kelvin. And we have worked through the units previously. We know that this is going to work out to kilograms per meter cubed. And when you get the value, it is 1.135 kilograms per meter cubed. Okay, so we have the density for A. I'm going to move this over just so I have more space. Okay, so air parcel B, we had temperature is the same, 30 degrees Celsius, and it's dry air. Okay, so now we need to calculate virtual temperature. So as before, it's going to be 303 Kelvin times 1 plus 0.61 times it's dry air, so the water vapor mixing ratio is going to be what? 0. So remember, W is equal to the mass of water vapor divided by the mass of dry air that it's mixed with. If there's no water vapor, then the numerator is 0 and the mixing ratio is 0. So we have that the virtual temperature is the same as the air temperature, 303 Kelvin. we then work through the density, 10 to the 5 pascals, divided by 287 joules per kilogram per Kelvin, times 303 Kelvin, and we get a density of 1.15 kilograms per meter cubed. So these are similar. Parcel A, they're both the same temperature, remember, but parcel A has water vapor and parcel B does not. So as expected, parcel B is more dense, 1.15 kilograms per cubic meter, more dense than parcel A, which is 1.35. Okay, so we have one more to do. And this was the one that we said was a little bit difficult because we didn't know how it was going to fall out, because we're going to have a temperature of 34 degrees Celsius, and that the warmer temperature would tend to make the air less dense than either A or B. On the other hand, this is dry air, and this one's moist, so moist air tends to be less dense. So they're counteracting factors here. Well, let's do the virtual temperature calculation. So we have TV is equal to, we have 307 Kelvin times 1 plus 0 again, because there's 0 water vapor in this air parcel. So the virtual temperature of this dry air is the same as its actual temperature, 307 Kelvin. Well, that's familiar. That's actually the same as parcel A's virtual temperature. If the virtual temperature is the same, then the density must be the same. So I could write it down, but I'd be writing down exactly the same numbers as this. The density of parcel C is 1.135 kilograms per meter cubed. Okay, so where'd the eraser go? Having done all that, that leads us to a few important insights here, important implications. So one is that when the virtual temperature is the same, between air parcels, their density is the same. Regardless of actual temperature or water vapor. So you can have a high virtual temperature by having a high actual temperature, or you can have a high virtual temperature by having lots of water vapor. It doesn't matter how you get that virtual temperature. If two air parcels have the same virtual temperature, they have the same density.
I was gonna ask, is that why it's like it feels hotter when it's like humid because of the water vapor?
Oh, yeah, great, good question. No. Yeah, so you might wonder, so we've defined this virtual temperature, and heat index is another thing that people talk about as being affected by water vapor. So they are similar in that respect. On a hot day, if you add more water vapor to the atmosphere, you get a higher heat index and you get a higher virtual temperature. That is where their similarities end. Both of them are increased by water vapor. Okay. However, we defined the virtual temperature based solely on physical properties of air and water vapor. We made no reference to how air feels or how humidity makes you feel. Those heat indexes that you see, those require calibrating by putting people in a room and exposing them to different levels of humidity and asking, how warm does it feel? So these heat indices are really about how temperature and humidity are perceived by people. Virtual temperature is a purely physical sciences concept. Nevertheless, both of them are increased by water vapor. So they're,
Okay, that works.
yeah. Virtual temperature is certainly not the same as the heat index. Another implication is comparing virtual temperature is the same as comparing density, or equivalent to. I should probably say not the same, but it's equivalent to. So you want to know which air parcel is more or less dense. Just calculate the virtual temperatures, and then whichever one has the higher virtual temperature is less dense. Now, there's sort of a third insight, which is a different way to think about this. So if moist air has a virtual temperature, TV, then dry air with the same density must have an actual temperature, TV. So moist air with virtual temperature TV has the same density as dry air with actual temperature so the actual temperature T equal to TV. And that's really just a result of how we defined virtual temperature. So virtual temperature is the actual temperature that dry air must have in order to have the same density as the moist air. Okay, so the next homework that you do will have some examples of calculating T and or virtual temperature and actual temperature. I think this is probably a good spot to end. I have just a couple of short announcements about Friday's class. I'm actually going to be out of town, and you're going to have a guest lecture from John Elquist, Professor John Elquist, and he's going to introduce the topic of hydrostatic balance in the atmosphere. So this is another topic. Virtual temperature is in chapter 3 of the textbook, if you want to review it there. Hydrostatic balance is the next section of the textbook as well. Yeah?
That homework will be posted.
Yeah, I still need to post it, I know. I still need to write it, so yeah, stay tuned. Yeah.
Is it always gonna be divided into the
Yeah, so the benefit of using virtual temperature is that you always use the specific gas constant for dry air. And so virtual temperature is just saving you the effort of ever having to recalculate the specific gas constant.
Wow.
Yeah, thanks, good questions.
Evan, say bye to your fans.